All right, teacher notes on atomic theory. When it comes to Dalton's law, Dalton came up with 4 different postulates about the atom. What I want you to know are the 2 that were disproven. When he said atoms are the tiniest the particles can be, that they are indivisible, that was disproven when J.J. Thomson discovered electrons. So atoms are not the smallest possible particle. They can get even smaller, like electrons, protons, neutrons. Okay? So J.J. Thomson's discovery of electrons disproves this postulate of Dalton's. Second, when we discovered isotopes, this disproved Dalton's second postulate that all atoms of a given element are identical in their physical and chemical properties. They're not totally identical because some of them have different masses. So the discovery of isotopes is going to disprove this postulate of Dalton's. Okay, next is J.J. Thomson. He discovered negatively charged particles called electrons with his cathode ray experiment. This is the cathode ray experiment. He then named his model the plum pudding model. This is the plum pudding model. In his model, there are negative electrons spread throughout in a sparse positive mass because he only discovered the electrons, but logically there had to be some balance of positive, and so he just said there's a positive sparse cloud that's positive and there are negative electrons within. In his cathode ray experiment, he brought magnets near the cathode ray and then the ray bent toward the positive plate. That's because it was attracted to the positive plate but repelled by the negative. Opposites attract, right? So repelled, attracted, towards, okay? And this is the effects. Then came Rutherford's gold foil experiment. He took J.J. Thomson's model and put it to the test. He believed with this model that if he shot positive particles through an alpha ray, alpha particle emitter, so alpha particles are positively charged particles, and he expected all of these positive particles to go straight through the gold foil, which would have proved J.J. Thomson's model. But since they did not all go through the gold foil, some of them were deflected sideways, some of them even reflected backwards, and because of this, it's been proven, Rutherford proves that actually all the positive is concentrated in the center in a dense positive mass called the nucleus. So he expected all the particles to go through, but actually most went through, but some were deflected by the gold foil, proving the existence of a dense positively charged nucleus. Please know that Rutherford came up with or proved the dense positively charged nucleus. Now use the notes on the history of the model of the atom and answer these true-false questions. First one, the plum pudding model showed a sparse positive mass, that is true, with negative electrons spread throughout. This is all true. Rutherford's gold foil experiment proved J.J. Thomson's model. That is false. It disproved J.J. Thomson's model. The gold foil experiment was conducted using a cathode ray. That is false. It was conducted using gold foil and an alpha particle emitter. Rutherford shot alpha particles at a piece of gold foil and expected to see all of the particles go through. That is true, and then hit the detector. So that is a true statement. He shot alpha particles at a piece of gold foil and expected them all to go through. Alpha particles are positively charged particles. That is true. The current atom has a dense positive nucleus with negative electrons on the outside of the nucleus. That is all true. Thomson's cathode ray experiment shows that electrons possess a negative charge, that is true, which are deflected by the positive plate and attracted by the negative plate. Opposites attract, so it should have been attracted to the positive plate and deflected by the negative plate. Those are opposite of what they should be, so this statement is false. Now we're going to focus on nuclide symbols. So for the record, you would take this symbol and you would write it. Then the atomic number is found at the top left of the box on the periodic table. That is the number you would put at the bottom left of the symbol. This is the atomic number. The mass number has to be given to you, but we'll take this average mass and we'll kind of round it off for just this moment and put this isotope as 24. Now, if I had a charge, I would place it in this spot right here. So let's apply this now. All right, so this 27 is the mass number of silicon. And I'm missing the atomic number, but we can find it on the periodic table. It is right here. It is element number 14 is the atomic number of silicon. So this should be a 14. That is the atomic number. The atomic number equals the number of protons. There are 14 protons because the atomic number is 14. Now, if I want to know the number of neutrons, I'm going to do 27 minus 14 equals the neutrons. 27 minus 14 equals 13 neutrons. Electrons, well, I have to look at the charge. There's nothing here, so the charge of this is 0 because there's nothing there. This is a neutral atom, and in neutral atoms, the protons and the electrons are equal to each other. Remember, protons are positive, electrons are negative, and so when we have an equal balance of positive and negative, we're going to have 0 charge. So there's going to be nothing right here. One more example, and then you will try some. This 15 is my atomic number, which is also my number of protons. This 31 is the mass number. If I do 31 minus 15, I can get the number of neutrons. 31 minus 15 equals 16 neutrons. And then to get the charge, I look here. This has a -3 charge, -3. So watch carefully. To get the electrons, it's going to go 15 plus 3 equals 18 electrons. All right, so now you guys are going to try these next 4, and then we'll go over the answers. For the record, this is the mass number for this fluorine isotope. You can get the atomic number from the periodic table, so they must be telling you the mass number here. All right, give them a try. All right, let's do this one first. Strontium does not have the atomic number, so I will go look it up on the periodic table. It is atomic number 38. So this has a 38 here. That is the atomic number, which tells me the number of protons. This 86 is the mass number, and if I do 86 minus 38, I get the number of neutrons, which I believe is 46. And then the charge is here. It's a +2 charge. Here's the trick. Watch carefully to get electrons. 38 minus 2 equals 36 electrons. This should make sense because we have 38 positive protons, 36 negative electrons, which means I should have an overall +2 because I have 2 less electrons than I do protons. All right, I do not have the atomic number of scandium, so I'm going to look it up right here. It is 21. So the atomic number here is 21. That tells me the number of protons. 46 is the mass number. The neutrons is 46 minus 21 equals 25 neutrons. The charge is a +3. 21 minus 3 equals 18 electrons. Remember, we have 21 positives, 18 negatives, which overall gives us this +3 charge. Selenium is atomic number 34. So that goes here. The atomic number is 34. That tells us the number of protons. The mass number is 79. 79 minus 34 is going to equal our number of neutrons, which I think is 45. Okay, and then the charge is a -2, so 34 plus 2 equals 36 electrons. This should make sense because we have 34 positives and 36 negatives, which gives us an overall -2. Fluorine is here. fluorine, and it has an atomic number of 9. So the atomic number is 9. That tells me the number of protons is 9. You can automatically tell that this is neutral, has a neutral charge, because it's in longhand form and they can't put the charge on this, or we don't put the charge on it. So it's assumed neutral, which means my protons and my electrons should be the same. Positive 9 against negative 9 equals 0 charge. And then the mass number is 19, and then I'll do 19 minus 9 to get my number of neutrons, which is 10 neutrons. We're going to do the reverse now. Write the symbol for an atom that has 50 protons. So protons identifies your element, so we have to go find atomic number 50 to see that the element is 10. So this is Sn. The protons is the atomic number, so that's going to go at the bottom left. To get this number right here, I have to do protons plus the neutrons. So 50 plus 68 is going to equal 118. And that's the mass number that goes right there. To get the charge, notice that I have 50 electrons, 50 protons, which means a positive 50 versus a negative 50 is a charge of 0. So this is the answer to what is the symbol for this atom. The symbol for this ion, that means it's going to have a charge. First, I have to go look up the number of protons, which is 27. So 27 is element, 27 is cobalt. So I'm going to write CO for cobalt, and 27 is the atomic number. That's my number of protons, goes down there. This number up here is my protons plus neutrons together. So 27 protons plus 34 neutrons is going to equal 61 mass number. Finally, what's the charge? And I have to compare protons and electrons. There are 27 positive protons and 25 negative electrons. That is an overall +2 charge, which means this should be a +2 charge. That's because it's an ion is why it has a charge. Now you guys try the two on the right and then see the answers. Okay, so now we're going to look at this one. 82 is my number of protons. That is lead. So it's going to go PB, protons, and that is the atomic number that goes down here. This number is protons plus neutrons. So it's 82 protons and 128 neutrons. So together that's going to make 210. 210. And then it tells you it's an atom, but you can see that we have 82 positive protons and 82 negative electrons, which is a charge of 0. So this would be the symbol for this one. For an ion that contains 35 protons, element 35 is bromine. So we're going to write Br, 35 is my atomic number. Protons plus the neutrons together are going to equal 80. And then to get the charge, I got to compare protons and electrons. 35 protons, 36 electrons means I have an overall -1 charge. So this is a -1 ion for bromine. Isotopes. Okay, isotopes are going to be atoms that have the same element, which means they have the same number of protons, which means they have the same atomic number. This is what is the same for isotopes. They have the same element, they have the same protons, they're going to have the same atomic number. What makes isotopes different from one another is going to be that they have different masses, because they have a different number of neutrons, which is going to give them different mass numbers. Notice that electrons are not a factor for isotopes. So we do not care about electrons when it comes to for isotopes. Isotopes, we only focus on protons versus neutrons. Okay, atomic number versus mass number. Let's look at some examples. All right, which of these would be isotopes of each other? So remember, if they're isotopes, they have to be the same element, which means they're going to have the same atomic number, which means they're going to have the same number of protons. These are all the things that are the same. If they are isotopes, what's different is going to be the number of neutrons or the mass number. That's what's different about isotopes. So protons are the same. So because these have the same protons, those are going to be isotopes of each other. Notice that their number of neutrons are different. So these Q and R are isotopes of each other. Okay, notice that has 12 protons, that has 14, so that cannot even be considered isotopes. Let's look at this second example. Among these four atoms, which ones are isotopes of each other? So the bottom numbers have to be the same when you're looking at this type of symbol, right? That's the same atomic number is what they have to have. And then up here they have a different mass number. Different masses. Okay, so same atomic number but different masses, and they have to be the same element to be isotopes of each other. Therefore, letter A is the correct answer, that these are isotopes of each other. Right, general symbols. A proton is going to be 1 over 1p. An electron is going to be 0 over negative 1e. A neutron is going to be 1 over 0n. An alpha particle is 4 over 2 helium. A beta particle is the same as an electron, 4 over negative 1e, and a gamma particle is going to be kind of like this little ribbon, and we're going to have a 0 over 0. Okay, how to write an alpha and a beta decay. Here's one example of each. Write the alpha decay of this. The alpha particle is a 4 over 2 helium, so you do need to memorize that. Then, what do we have? If this loses a 4 over 2 helium, we end up with our mass is 4 less than it was before, so my new mass is 234, and then this is going to be, the atomic number is going to be 2 less than what it was before, because we're going to lose 2, so that makes my atomic number 90, and then I can come on the periodic table to look at element 90 is thorium. So this is thorium, and that is the alpha decay of uranium. It's going to have, notice that these two added together equals 238, and these two added together equals 92. A beta decay is where you emit a beta particle, which is a 0 over negative 1 electron. The mass number is not going to change because this is not going to lose any mass when it loses an electron, so the mass number stays the same. The atomic number, on the other hand, is going to go up by 1. That seems weird, but 91 minus 1 equals 0. And then atomic element number 91 on the periodic table is Pa, protactinium. So Pa. So you try the next few. Okay, the alpha decay of this, we're going to emit a 4 over 2 helium. My mass will go down by 4. And my atomic number will go down by 2. Element number 97 is Bk, berkelium. Here, this is a beta decay, so we're going to emit a beta particle. The mass will not change. The atomic number will go up by 1 because 101 minus 1 equals this 100. And then element 101 is Md, that's mendelevium. Alpha decay, give off a 4 over 2 helium. This is going to go down by 4 and become 218. 86 minus 2 is going to give me 84. And element number 84 is Po, polonium. This is a beta decay, so we're going to give off a 0 over negative 1 electron. The mass will not change to 28. The atomic number goes up by 1. And then element number 90 is Th, thorium. Okay, which has a greater penetrating power than an alpha or a beta decay? What I want you to know is that alpha is weaker penetrating power, and that beta is the stronger penetrating power. Focus on those specific words. That alpha is a weaker penetrating power, and beta is a stronger penetrating power. To illustrate penetrating power, alpha is very massive. It cannot even go through paper, so it doesn't even go through your skin, and so it goes through the least amount of objects. It has the weakest penetrating power. Beta has a stronger penetrating power. It can go through paper, it can go through your skin. It's stopped by a sheet of metal like aluminum foil. And then gamma radiation has the most penetrating power. It can go through just about everything because it's basically pure high energy. Compare nuclear fusion and fission. Nuclear fusion, fuse means to combine or come together. We're going to take two very light nuclei. These are both hydrogens. They will come together and fuse and become something slightly heavier, like helium, ever so slightly heavier. So they combine, light combines to form heavier. It's going to give off energy. This is what occurs in the sun. Nuclear fission, fission is division. Heavy nuclei split to form lighter nuclei, the reverse or opposite. It is going to give off energy. Both of them give off energy, and we use fission in all nuclear power. And this concludes all level 1 notes.